Hi everyone, and welcome to the third basic LS-DYNA tutorial. So in this example, we're gonna have a soft body impacting a rotating part. Okay, uh, this is a simulation of a simple bird strike problem. What is a bird strike? If you don't know bird strike problem, it's happened in the aerospace applications when the bird or a very soft body hits the airplane. So the first thing that we're gonna do today in this tutorial is we're gonna import that part of the airplane, and this part of course you can download it online, and this is the one. This is the propeller or the blade of the airplane. Okay, so you open this one. It's available in the GrabCAD community. You have to log in, of course. Sign up is free. Then you download the IGS file. So after you download it, you open the prepost and click on file, then import IGS. Then here is the file, carbon 5 by 3 finish.igs. Open. Okay, now you have this small window here. Specify unit and click on meters. Okay, in this problem we're gonna work on meters. Unlike the previous tutorials, in this one we're gonna try and do the simulation with different unit systems, and for the dimension we have meters, and click on OK. Okay, so you hold the control button, then with the mouse you hold also to rotate. Okay, so as you can see, it's a 3D model. So we're gonna do the same trick as before. Click here, element and mesh, then auto measure, and we mesh only the surface. Then after we mesh the surface, we mesh the surface as a shell. Then we input the thickness of the shell. Okay, so this one we will make it 0.0025, which is 2.5 millimeters, and mesh. Then click on accept. Now you have this mesh. Okay, so you no longer need the IGS file, so we don't need the IGS files anymore. Okay, since we have the mesh. So to delete them, we go to geometry tools, and here delete entity. So remove all. Yes. Okay, so now we don't have the IGS file, we have only the mesh, and close. Alright, so now we gonna do first, go here to the keyword manager and click on all. We're gonna define the section of this blade or this propeller section, and shell. Okay, new ID. Here I put it as shell. Then the thickness, they say the thickness of this guy is 1 mm, which is 0.001. Hit on the enter, then click on accept. Done. Okay, we go up, and this one is we're gonna define the material of this blade or this part. Okay, we're gonna make it a rigid body, so click number 20, rigid, then click new ID, then here we say blade or propeller or whatever. Okay, now the density we're gonna make it steel, so 76 or 7860 kilogram meter cubic. Okay, we're gonna work on these units. Just now the length is meter, the mass is kilogram, so the density kilogram per cubic meter. Alright, the young modulus gonna be in gigapascal, so 200 gigapascal. Poisson's ratio is 0.3, and click on accept. Alright, now as we said before, this blade gonna be rotating. Okay, and it will be rotating around the Z axis, of course, and it will not be allowed to move in any other direction. So we can put the constraint here. Okay, so see this one, center of mass constraint, we make it equal to number -1, and here just ignore it. Here you will put 111, then 110. What does this mean? Okay, 1 means it is constrained, 0 mean it is free and not fixed in that degree of freedom. So here the first 1, 2, 3 meaning it is fixed in the x and y and z translational direction, meaning it cannot move along the x, y, or z. Then you have this 1 and 1 meaning it is not allowed to rotate around the x or y. And the last one here is 0 meaning it is permitted or allowed to rotate around the z axis. And click on accept, then done. Okay, now we go to part. We link between the section, the material, and the part. So this one, the first, I rename it. The first thing I do, I rename it as blade or propeller or whatever. Then section ID. Okay, the section is shell, which has 1 mm the thickness. Material is the blade, which is rigid and it is fixed and only permitted to rotate around the z axis. Now accept and done. Okay, now the third. Okay, we are done one part. Now we're gonna make the rotation of this part. So click on all, then we need to define the velocity or the acceleration profile of the rotation. So we do that from define curve, the same way we did with the tension test. Here, new ID, I call it angular velocity or omega. Okay, so the starting velocity is 30 radian per second. Insert, and it's gonna be fixed throughout the simulation. And insert, accept. You plot here to see the velocity profile. Okay, the starting is 30 and the ending is also 30. This is I put it as 1 because meaning it's 1 second. Our simulation will take, of course, less than 1 second. Okay, so I close here. Now I go to boundary to define to impose the rotation. Define prescribe motion rigid. We don't select set, we select rigid because this is a rigid body. So this one part ID is a blade, of course. I click new here, rotation of propeller. Degree of freedom, I click here 7. You scroll down here to see what is 7 z rotational degree of freedom. Yes. Velocity, acceleration, or displacement, this curve that we defined just now is velocity. So here we select the curve just now, and for the time being click on accept. We're gonna have a small modification after this, but later. Okay, so right now this will rotate. So the next step is to make the bird part, or the part that represent the bird. As I said, this gonna be a very soft material and it will have a big deformation. So because of that, we will not make it from elements or shell or solid elements. We will make it from particles or nodes. So to do that, you go here, element and mesh, and go down here, SPH generation. SPH stands for smooth particle hydrodynamics. Okay, so create, you have many options here. I click on sphere. Okay, so what is the center of this one? Okay, in X gonna be 0.075, meaning 75 millimeters. In Y gonna be minus 0.25. In Z is 0, and R is the radius. So the radius, let's say it's 10 mm, 0.01. Okay, now what is the density of these particles? Let's say the density is 1000, and hit on apply. You see is the part is very far. Actually, I made a mistake here. Is 0.025. So just reject and apply again, and you see it is nicely here. Okay, and also reject accept. Why? Because here you see you have only one particle, because I did not define the number of particles in the three directions. So I reject again, and here let's say I put 20, 20, and 20. Then click on accept. You can see here you have the particles, and apply, then accept. Okay, done. Now we're gonna define the section of this one. Okay, it's not shell and it's not solid, it is SPH. So here down under the section you go until you find SPH. Okay, new SPH section. Okay, just stick with the defaults, they are good for most applications. Accept. Alright, so done with the section. Now is the material. Okay, the material, we're gonna select a very soft material, or we want this one to behave as a very soft material. So in the material we go and select number 9, which is null. So here I say bird material. Okay, so the density is 1000. This one, the cutoff pressure minus 1e6, and this mu viscosity coefficient 0.1. Okay, is it correct? Yes. Okay, and accept, and done. Okay, this material model, null material model, requires an equation of state. Equation of state is an equation that relates between the pressure and the volume of the material. So under the equation of state, EOS, I select this one, Grunissen. Okay, so new, I say bird equation of state. Okay, so the first parameters, C, I make it 1647, and the second one, S1, I make it 2.48. For the meaning of these parameters, you can refer to the theory manual of LS-DYNA. Click on accept. Done. Okay, now we link between the material, the equation of state, and the section to the part itself. So click on part. Okay, this blade is done already. SPH node, I call it bird. Okay, the section is SPH section. Material is a bird material, which is null material model. Equation of state is here, and click on accept. Okay, alright, so now if you see here, okay, the blade will rotate, but it will only partially hit the SPH part. So what we want to do, we want this SPH also to move upward in the Z direction. So I click on initial velocity generation, and all of you know this already. Sorry, here the set type, part ID, and I select on bird. Done. Okay, I want it to move in the Z direction with the velocity of 2.5. Then click on accept. Done. Okay, one note, if you see here, this one, the SPH particles will move in Z, which is correct. But if you notice just now, when we define the velocity, or when we define the rotation, we will say this blade or this propeller will rotate around the Z axis, and we put that omega, or the angular velocity, as positive. So this one, this means it will follow the right hand rule and rotate counterclockwise. Okay, so if it's rotate counterclockwise, then this blade, this part, will just go away. So we need to minus or reverse that direction of the rotation. So again, I click on boundary, prescribe motion. Here I have the load curve scale factor, and I just put a minus here. Okay, So the curve is 30, the velocity is 30 radian per second. Now it will be minus 30 per second, and accept and done. Okay, so now we need to define the interface or the contact between these two parts. So to do that, before we did it from contact automatic surface to surface. Okay, but now we don't have two surface. We have, this is node and this is surface. So we have automatic contact automatic nodes to surface. Click here. Okay, remember it says nodes to surface, so the slave must be always the nodes. Okay, so here the slave type should be number 4, set of node, and we did not define it, but it's okay. You click here and it says you did not define yet, so we define it. We create new from new entity option. So new entity, now we have this interface. You click on this small window and you select by part. Click on the part and all the nodes will be selected, and here you just rename it if you want. If you don't want, it's up to you. SPH node set, then click on apply. Alright, so it's selected already. Here you have SPH node set. Okay, now the master is the part, is a part, so you put number 3 and you select the blade. Okay, so here you name it contact propeller to bird and hit on the accept. Done. Okay, now almost done. We go define the output database D3 plot. In the interval you put it every 1 second. Every 1 millisecond. Accept. Okay, now you close this one. All, you have control to define the termination time. You click, you scroll down. Here you have termination. The end time you put it 0.00 or 0.4, 40 milliseconds, and you click on accept. Then here you need a new you need an extra control keyword. Here control SPH, because you are using SPH. This one you change it to 3 because you have a 3D problem. The rest just leave them as default, should be okay. Accept. Alright, so I think that's all. So you go here, save as, then you browse tutorial number 3, then you click word strico.k, or no need for .k, so it will be by itself, it will be .k by itself. Click on save. So birdstrike.k, you open this one, you run, start the input. Here is the file that we just made. Open, here you put 8 and you run. Okay, so now you have 5 minutes. So just wait for 5 minutes. Okay, done in 3 minutes 54 seconds. Okay, so now we want to see the results. Okay, so I minimize this one, I open, I have the results, I drag to here. Okay, so we see what will happen. So this is the results. Okay, the blade gonna cut the bird into 2 pieces. Okay, you can here, let's say, click on the plastic strain or the stress. Okay, alright, so I think all of these things you already know. So now what we're gonna do now is related to the SPH. You see the results are in particles, so how to represent them in a better way? You click here on setting, under the post processing, click on setting, then you have SPH particle. Okay, instead of point you click on smooth. Okay, click on apply. So now you see you have bigger particles, so to make the representation nicer. And of course here you can control the divisions of the spheres. If you make it 4, it will be a bit rough. If you make it 24, it will be very smooth. Okay, and here of course you can control the size of the particles. So now it's very big, very fat particles, no too much. Okay, like this is okay. So now it will be a bit slower, of course. Okay, so that's all for this tutorial. Thank you very much and see you next time.